Welcome to today's Explainer. We're diving straight into a topic that's absolutely critical to the electrical integrity of modern infrastructure, yet, surprisingly, it's often completely misunderstood. We're talking about specifying cable trays. Now, picking a tray to hold some cables might seem like a straightforward catalog purchase, right? Just grab one that fits. But treating it that way is a massive liability, one that literally costs facilities millions in hidden lifecycle repairs. So get ready to take some mental notes, because we're going to break down the highly practical framework that professional engineers use to get this right every single time.
Okay, let's dive into this fundamental shift in mindset you need to have. The naive way of doing things is what we call the single variable approach. That's basically just flipping through a catalog and picking a tray based on immediate price or basic dimension. But reality demands a four linked decisions mindset. It's a complex, interconnected engineering process. You really can't just make one choice in a vacuum without it impacting the whole system.
And the stakes for getting this wrong are incredibly high. The danger isn't usually some catastrophic failure on day one. The real liability is the rework that starts showing up months after the project has been handed over to the client. We're talking about sagging trays, compromised cable integrity, and massive, costly retrofits. Actually, scratch that. It's more like a ticking time bomb of liability if you don't use a structured engineering approach right from the starting line.
So, to avoid those exact costly mistakes, here's our roadmap for today. 1. Avoiding costly handover rework. 2. The four-step selection sequence. 3. Designing for future capacity. And 4. Meeting global engineering standards.
Let's jump right into Section 1, avoiding costly handover rework. Listen, a simple assumption early on can completely ruin a project's timeline and budget down the line. We have to engineer those failures out of our process by really grasping linked decisions. This is the process of getting the environment, geometry, load, and maintenance strategy right, all together. You literally cannot separate them. It's like a giant puzzle. If you change one variable, you fundamentally alter all the others. It creates this massive domino effect. If you change the geometry without considering the load, or say you ignore the maintenance strategy when evaluating the environment, you're practically guaranteeing post-installation failures. It absolutely has to be a holistic, unified decision.
Moving on to Section 2, the four-step selection sequence. Now, what's really interesting about this is the practical, field-tested framework from Xinma that completely solves the rework problem. It gives us the exact sequential order required for a proper specification. Step 1 is environment, Step 2 is geometry, Step 3 is load class, and Step 4 is maintenance strategy. Now, environment must always come first, no exceptions. You have to know the physical realities. We're talking corrosion risks, temperature extremes, indoor versus outdoor, before you can even think about the shape of the tray. Only then can you move down the line. Skipping a step or even just reordering them completely breaks the entire engineering logic.
Let's look a little closer at Step 2, geometry, because this is where a lot of people trip up. You generally have four main options fitting different cable functions: ladder, perforated, solid bottom, and wire mesh. Each serves a very specific purpose, but here is the critical warning. If you switch the tray type, say you go from a solid bottom to a wire mesh, without rechecking your span, you will completely alter the load class. Remember, it's a linked decision. You can't just swap shapes and assume the physical support structure will hold the exact same weight over the exact same distance. It just doesn't work that way.
All right, Section 3, designing for future capacity.
We really need to shift our focus from just the immediate installation to the long-term life cycle of the route. So the crucial point is that fill, span, and future capacity all interact in this constant mathematical tug of war. The amount of cables you put in the tray, the distance between your support spans, and the room you'll inevitably need for future upgrades, they all have to be perfectly balanced. If you max out your fill today, you completely ruin your future capacity, and honestly, you might even overload your span right off the bat.
To put that into perspective, the golden rule of specification is designing to roughly 40 to 50% fill at commissioning. For instance, designing to a 45% fill leaves a solid 55% for future capacity and protection. And let's be clear, leaving this empty space is definitely not a waste of money. It's exactly what protects the route long term. It allows for necessary heat dissipation, reduces electromagnetic interference, and critically, it gives you room to pull new cables years later without having to tear down the whole shebang and start over from scratch.
And keeping with that theme of the long-term life cycle, the real money on a project isn't saved by buying a slightly cheaper tray up front.
The real savings come from making smart installation decisions and access decisions before the specification is even frozen. If you plan out exactly how the maintenance crews will actually physically access the tray to add those future cables, you drastically reduce the life cycle cost of the facility over the next 10, 20, or 30 years. Planning up front is absolutely everything.
Which brings us to our final part, Section 4, Meeting Global Engineering Standards. We need to ground all this theoretical framework into industry reality. Xinma, the manufacturer behind this guide, maps their specific product lines directly to highly demanding target industries. They manufacture cable tray systems, busways, seismic bracing, and intelligent cable management solutions that are perfectly tailored for data centers, rail transit, industrial plants, and commercial buildings. When you're operating in these heavy-hitting sectors, the four-step sequence we just talked about isn't just a nice-to-have. It's mandatory for safety.
And because safety is non-negotiable, compliance is paramount. You need to know the exact global standards these systems comply with. We're talking IEC 61537, NEMA V1, BS-EN 50085, and GB 31251. Seeing these specific standards should instantly build trust. It means those interconnected decisions we discussed regarding environment, geometry, load, and maintenance, they've all been rigorously tested and verified to ensure maximum safety and reliability on a truly global scale.
So, as we wrap up today's explainer, I want to leave you with a bit of a provocative question. Ask yourself honestly, is your current cable tray specification genuinely protecting your route long-term, or is it just hiding future rework? Are you still making a single variable choice, or are you finally making four linked decisions? I really hope this framework helped you rethink your engineering sequence so you can build infrastructure that truly stands the test of time. Thanks so much for joining me today, and as always, keep learning.